So the first talk after the lunch is Ariel Gabizon. He's going to be talking about splitting up SNARKs with cached quotients. Welcome him to the stage, please.
Thank you. So like the title says, the focus of the talk is a technique called cached quotients. But I want to start by sort of casting that work in zooming out and sort of a description of what's been going on with pairing-based SNARKs in the last decade or so. So we can think of it as the pairing-based SNARKs triology, where the first episode, A New Hope, was Jens Groth saying, look, we've got these cool things called pairings, and we can get proofs like with constant number of group elements without all the complications of what's called the PCP theorem that SNARKs were based on back then. And then the pivotal moment in this sort of chapter was GGPR that introduced QAPs that then were dubbed R1CSs, and that work sort of said, look, you know, this can really be practical. And Groth 16, which we all know, sort of optimized this approach. So this was sort of a chapter where we said, let's basically do everything with pairings. The second chapter, the polynomial commitment scheme strikes back, was saying, yeah, pairings are great, but actually, if we sort of restrict our use of pairings to just this one cryptographic component, what probably most people here are familiar with, a polynomial commitment scheme, we can suddenly get a lot of flexibility, and this is what gave us SNARKs with a universal setup instead of setup per circuit, which was a logistical nightmare. This was what helped us get custom gates that we all like. So this is all pretty good. And the third chapter, which we're sort of starting recently, we've started, Return of the Pairing, started with this work called Caulk. And you could think of it as just sort of going back to a middle ground where, okay, we don't have to do everything with the pairing when it's not convenient, but maybe there's places besides the polynomial commitment scheme where we can get some power out of the pairing. And Caulk and other, is this work that started showing, yes, we definitely can. So before starting to describe this sort of third chapter of this triology, let's do a short KZG recap. So the KZG polynomial commitment scheme, which I imagine most of you are familiar with, the basic idea is this is what's called the trusted setup. We generate somehow in a protocol a string of group elements where in the exponent or in the scalar we have the powers of some secret x. And then this gives us a way to get a short commitment to a degree D polynomial. What is the commitment of the degree D polynomial? It's simply f. It's simply f of the secret x encoded in the exponent or in the scalar. So KZG commitment scheme, probably most of you know, is incredibly useful. But really for the talk, if you're not too comfortable with it, the two cool features of KZG that we'll need are the following. So these two features, you try to engrave them in your mind. The first one is linearity. The commitment of the polynomial f plus g is the commitment of f plus the commitment of g. The second, more fancy property is that using the pairing, we can do product checks directly between commitments. So say now I have commitments to 4 polynomials, f1, f2, g1, and g2. Then I directly, from the commitments, I can check whether the polynomial f1 times f2 is equal to the polynomial g1 times g2. And the thing that may confuse you if you're familiar with pairings is like, okay, I can see how you compare the commitments using a pairing, but you're saying that means the polynomials that are identical as polynomials. And here we use this strong assumption, the algebraic group model, which lets us conclude that yes, if we can actually conclude from this check that the polynomials are identical. So those are the two nice features of KZG as a polynomial commitment scheme, the linearity and the ability to perform product checks. All right, so now that we did that recap, we can describe the first chapter of the first part of this third chapter of pairing-based SNARKs, so from Caulk. So we can think of the following question. We have a vanishing polynomial of some subset T. And we have some polynomial f. The verifier has the commitment to this vanishing polynomial zt and the commitment to f. And now the prover wants to convince the verifier that this f is actually the vanishing polynomial of some subset S that is contained in T. So if you've played around with quotients, KZG, you can probably think of how you would do this. And the natural way to do this would require an amount of prover operations that depends on the size of T, or let's say T minus S. And the cool thing that happened with Caulk is they can do this with only order S operations, right? So think of S being much smaller than T. Caulk was able to do this in order S operations. So how does this work? I won't go, I'll only sketch this because I want to save your brain power for the cached quotients method that I want to explain, which is something a bit different. So actually I'm going to skip how this thing works, and if there's time or someone asks me, we'll get to it in the end. But again, the cool thing that started this new chapter of pairing-based SNARKs is that this requires only order of S, not order of T operations. All right, so now let's talk for 1 second about sparse polynomials. What do I mean by sparse polynomials? So for the rest of the talk, keep in your head, we always have two parameters, little n and big N, and little n is naturally much smaller. So what do we mean by sparse polynomials? So think that we always have some fixed set of polynomials, like capital N polynomials, B1 to Bn. And what do we mean by a polynomial A being little n sparse in the base B? Right? We simply mean that we can write it as a combination of at most little n of these BIs. Right? So we can write it like in this way where only little n AIs will be non-zero. Okay, so that's sparse polynomials. And most of the time, but not all of the time, as we're going to see in this talk, what is this B? It's going to be just the Lagrange base of some subgroup, right? So the sparsity corresponds to the polynomial being mostly 0 and some subgroup. So sparse polynomials interact nicely with KZG. Why? Because we can pre-compute the KZG commitments of the basis elements. And later, during a protocol, when the prover has some little n sparse polynomial A, from the linearity of KZG, they can compute the commitment to A in just little n operations, right? Because they're just going to combine the commitments of the BIs that are used in A. All right, and now we finally come to this cached quotients method. So what is the scenario generally? We're going to look at concrete applications like lookups later, but what is the general scenario we're looking at with cached quotients? So the scenario is like this. We have some prefixed preprocessed polynomials t and z, where the degree of z is capital, is big N, and think also of the degree of t as something of that order, something big. And now the prover has as an input an n sparse, little n sparse polynomial A, and some polynomial R of degree smaller than big N. And the verifier has the commitments of these polynomials. And now what do we want to do? The prover wants to convince the verifier that A times T, so A is the sparse prover polynomial again, T is the pre-processed polynomial, that A times T is equal to R mod Z. And the punchline is that we want this to be an O of little n operations. Okay, so all of these polynomials in this equation, they're of degree typically big N. And we want to do this, the punchline, the point is we want to do this in O of little n operations. All right, so what's the natural way we prove things like this? Right, we use quotients. So we know that A times T is equal to R mod Z, if and only if there exists some quotient polynomial Q such that A times T is equal to ZQ plus R. And again, Q is going to be of degree something like big N, typically. The point is, we're going to be able to compute the commitment to Q in only little n operations. So how do we do this? First, we're going to have a pre-processing stage where for each I, we're going to compute the commitment to a polynomial qi. What is the polynomial qi? It is the quotient that comes up when, for the I basis element that A is sparse in, we multiply by d and divide with remainder by z. So right, so B1 to B big N, that was the basis in which A was sparse. And Qi is the polynomial such that for the ith basis element, Bi times T equals Qi times Z plus some remainder, Ri. And here's where the name cached quotients comes from. So the cached quotients are the commitments to these QIs. Where again, what are these QIs? They're exactly the quotients when you divide with remainder the basis elements in which your input polynomial is going to be sparse. And yeah, we're also going to pre-compute the commitment to this z and d, the t that we're multiplying and then dividing by, right? Remember z and t, this method works when z and t are predetermined. So basically, right, the reason we can do this is that a technical way to say it is like division is a linear operation, or a consequence of that, or another way to say it is that Q is going to inherit A's sparseness. If A's sparseness was in this BI basis, Q's sparsity is going to be in this QI basis, right? So more precisely, to remind you again, A is this sum AI BI, where most of the AIs are 0. So Q, you can check just from the linearity of division, is going to be sum AI QI. And therefore, after we've pre-processed the commitments to the QIs, the prover can compute now the commitment to Q in only little n operations. Right, this AI not equal to 0 is a little redundant because, well, obviously it's redundant because the zeros wouldn't change the sum. Okay. And now we come, all right, so what's the situation we're in? We want to check that A times T is equal to Q times Z plus R, where we don't actually have Q, we only have the commitment to Q. Actually computing Q would be too expensive for us. But here's where the second nice property of KZG comes in, that we went over in the beginning, that if we have an equation of degree at most 2, we can directly check it on the commitments with pairings. So given only the commitment to A, T, Q, Z, and R, we can, the verifier can check that this equation holds, which, whoops, what happened? My monitor, okay. Which exactly, exactly implies what we wanted, that A times T is equal to R mod Z. So, so that's basically the cached quotient method in like an abstract, general setting. And now let's look at two concrete concrete cases where this has been used. So the first time this was used was in a paper called CQ, which just stands for cached quotients, with Dario Fiore and Liam Egan. So what's the lookup problem? You're probably familiar. We have some preprocessed table T of size big N. We have some witness F of size little n. And we want to check that all the elements of the witness are in the table. We want to prove that. And the very interesting result of this line of works that started with Caulk and culminated, at least currently, in CQ, is that we can do this in prover time little n time log n. So we can do lookups in prover time that, after preprocessing, doesn't depend on the table size. So for big tables, this is a pretty big improvement over lookup that required capital N log n operations. So I'm going to concentrate on a second application. So the very sketchy sketch of this why this works is that if we use the log derivative lookup, that there was a very nice talk by Ulrich about it earlier this morning. If it ends up being that what you're doing there is multiplying some sparse polynomial, that sort of representing what values are actually used from the table, times a preprocessed polynomial, a polynomial representing the table. And this is exactly a good fit for this cached quotient methods, right? If we multiplying a sparse polynomial by a preprocessed polynomial, the cached quotients method allows us to do this where the number of prover operations only depends on the sparsity. Right? So this proof sketch is what appears in the CQ paper in greater length. And now application 2 from a more recent paper with Liam Egan called CQ Lin. What is the time situation? 5 minutes. Okay. So I'm actually gonna get a little technical now. So apologies if this part is going to be not totally followable. So what is the lincheck problem? So we have some predetermined fixed n times n matrix. We have some prover polynomial. The verifier has the commitment to it. And let's call A just the vector of values of this polynomial on some subgroup of size n. So from now on, the big N is going to be little n squared, and it won't be explicitly on the slides, in some sense. And what do we want to do? The prover wants to show that m times a is 0. And again, the punchline is he wants to do it in O of n operations, even though the matrix could have n squared non-zero entries. And for the next slide, let's let L1 to Ln be a Lagrange basis for H. So I'm going to reduce this problem to the sort of cache quotient. I'm going to massage it into the cache quotients setting. So this will be a little technical, apologies. we're going to represent the matrix by a polynomial of degree roughly n squared. So it's the polynomial mij, where the row is going to be multiplied by the Lagrange, but with x to the n inside, times Lj of x. So this is the polynomial representing the matrix. Think of the x to n, it might help to think of the x to the n as y. It's just another variable y, and then this expression maybe is easier to digest. And really in early drafts of the paper it was y. And now let z be the polynomial x to the n squared minus 1. And let a be sort of our input polynomial, but with a raised to the power n inside. So a is like f of x to the n. And now finally let r be like a times m mod z. So the idea is this a times m is sort of a polynomial representation of the vector matrix multiplication. And if you sit with a paper in pen, you can see that R is going to have this form. And of course, it's a lot to digest. What I want to highlight is that if you look at the inner sum, that is, that's sort of the expression you want. That's like the ith row of the matrix times the vector A. It's almost what you want, but it has this annoying Li of x to the n, right? So if we didn't have that annoying Li of x to the n, this R would be 0, right? In the case that the prover is honest and the matrix times A is 0, this R would all be 0. Right, so like I said, so m times a, okay, but we could get rid of this Li of x to the n. If we mod it out by x to the n, this Li of x to the n would become some constant. It would become like 1, just a constant 1 over n. So we have that m times a is 0 if and only if this R is 0 mod x to the n. Okay, and now we want to show that this is a fit for the cache quotients method. So the first thing to notice is that this A is sparse in like the basis of the Lagrange polynomials, but applied on x to the n, right? Because again, A was just f of x to the n, so it's gonna be this. It's just this polynomial of n powers, so it's going to be sparse in this base. So basically, we're going to use the cache quotients method twice. Once to show that the remainder we committed to is really correct, that A times m is equal to R. And the second time to show that R is 0 mod x to the n. And an important point, sort of what we said was like we can use this method when the not fixed polynomial is sparse. And again, the point is because of the linearity of division, if we start off with a sparse A, R is going to be sparse in an appropriate base of remainders that, when you multiply, remainders like in multiplication of m mod z. Yeah, so I'm like more or less on 0. All right, so yeah, so anyway, I'll stop here and thanks, and I'm, I guess, open for questions if there's time. Yeah.
I think we can take like one question for good measure, and the rest just hook up with Ariel afterwards.
What do you use the lincheck protocol for?
We haven't used it yet. I think it could be good for ZKML applications where you have a lot of multiplication by matrices that are potentially dense, like as opposed to matrices you get from R1CS that are very sparse. So ZKML in one word. Yeah.
Thanks.
Right, we have to rush to the next talk, but please feel free to talk with Ariel afterwards. Thank you very much, Ariel.
Thank you.